Ladies and gentlemen, now thank you for turning up to this month's webinar and see a few familiar faces that Fred pointed out. When I say familiar faces, I should say familiar handles. And this webinar is going to be a little bit easier, hopefully. There is a workbook or guidebook that comes with this webinar. I'm actually going to ask you to not look at it during this webinar because we're going to actually work together through a couple of problems. And one of the best ways to learn is to see something, and when you get asked the question, have a go at coming up with the answer in your mind, and feel free to share it amongst the group as well. If you don't feel comfortable, that's fine, but come up with an answer or what you think might be explaining what's going on. When you're first starting out this process of reliability engineering, you're almost certainly going to be wrong most of the time, as everybody else is. You're not by yourself in that regard. But the reason why you should come up with an answer in your own mind is because it's a really useful learning tool. You can, if you want to, go through the workbook and the guidebook and turn ahead and see what the answers to or what the deductions we can make from each plot we're going to look at today are, but that doesn't help you learn. Try and put yourself out there a little bit, even if it's only a private conversation in your own mind, because we're going to try and work out what's going on with some certain things as they relate to reliability. Now, I know it's a pretty vague introduction, so let's look into it and start with a scenario that some of you who have done some of my previous webinars will be at least a little bit familiar with. Now, this is a great big mining truck. And when we say big mining truck, we mean really big. It has a 400-ton payload, and these trucks often get driven non-stop. The only times they stop is for maintenance, with a lot of operations officers only allow through gritted teeth because they want these things to be driving non-stop, making money. And they cost in the vicinity of $5 to $6 million US. And of course, big trucks require big engines. And so the heart and soul of this truck is this monstrosity of a machine right here. And this is a big engine. It's bigger than many buildings for that matter. So it's a really big engine. It's a 20-cylinder engine, which often costs between $700,000 and $800,000 US. So obviously, if you're in a mine or an operations officer or a manager or a maintenance team leader, whatever your position is that you can imagine yourself being in when you look at this sort of machine, of course, you are interested in the reliability of this machine. And as we talk about a lot during these webinars, you can be interested in measuring reliability or improving reliability. And as a rule, improving reliability is much better than measuring reliability. So this webinar is, for some of you who looked at the title, and remember what the title is all about looking at this thing called a Weibull probability plot. Some of you might not know much about probability plots. And this webinar is not going to give you all the information you need to become a master of probability plotting. It will benefit you if you do have some idea about what a probability plot is. But if you don't have a good understanding, as long as you've got a baseline understanding of reliability statistics, hopefully you will get something out of this webinar. And the reason why I'm talking about this thing called probability plotting is because probability plotting, specifically Weibull probability plotting, is a very powerful tool in reliability engineering, and it helps us answer questions like, how does the reliability of our system behave? And that might seem like a very trivial question, but reliability can mean lots of different things. How long it will take before we expect 5% of our engines to have failed? How many engines do we expect to have failed after 1 year of operation? There's so many different variations to questions that are simply based on what is the reliability of this thing. So the behavior of reliability is actually very important. And again, for those veterans of my webinars, I'm going to bring back the good old favorite, the random hand of failure, which for those of you who don't know is the way I at least try to represent all the different factors and variables and uncertainties and things that are otherwise going to introduce randomness into a process. Even if you are of the school of thought that there is no such thing as random, if we were to hypothetically know the position of every single atom and electron and every force and every little current and everything else associated with something as complex as a machine, we should be able to predict with absolute certainty when it's going to fail. That could be technically true, although that hasn't been proven yet. In practice, we will never know with absolute certainty the location of every single atom in the machine. And even if we did, the computational power required to actually predict based on a precise knowledge of customer or user use, such that we can, with absolute certainty, know when our thing is going to fail, is many centuries away. So in practice, these machines are essentially identical to us. They look the same, they sound the same, they feel the same, they're manufactured by the same organization, even though we know that there's going to be microscopic differences. So in practice, we are dealing with this thing called a random process with all these different factors affecting how long it's going to take for our thing to fail. And let's just say we have some data from the field, from a test, from a vendor, where we have specific times to failure for our engines. Now, each blue dot here represents how long it took before one of our engines failed. And these blue dots, you can see there's a bit of clustering going on. So maybe you can say, oh, okay, well, there's clearly some sort of trends happening. The problem with this is that you only have, or you can only see, I believe, 28 data points. Thing is, this was data pulled from the field, and there are 78 engines that contributed data to our current data set. What that means is that there are plenty of engines out there that haven't failed, and those engines that haven't failed, although they don't get a single dot on this line or arrow, they are actually very important to take into consideration. And so for many reasons, including that, we often take data like this, and instead of just simply looking at all these points on a line or an arrow, which represents time to failure, we create a chart which looks like this. And this chart is essentially the CDF chart. So I'm not going to go into too many details about probability and statistics, but suffice to say, the CDF, the cumulative distribution function of a probability distribution, is analogous in this context to the percentage of things that have failed. So on the vertical axis, you can see a scale from 0 to 100%, and a CDF value of 60% implies that we would expect at that point in time or usage, 60% of our engines to have failed. Now, one of the reasons we like these CDF charts is because when we plot data like this, we'll move from left to right, more and more engines are failing, you can see a smoother line. It's all well and good to be able to see densities or be able to subjectively assess how tightly clustered these data points are on the arrow. But as soon as we put it in a CDF plot, it creates this trend, which is much easier for us human beings to start to process. Now, the other thing is, remember how I said there's 28 times to failure and 50 what we call right-censored data points. So there's 50 engines which are still happily working away. Those 50 right-censored data points, those 50 engines which are still working, which haven't failed yet, they need to be taken into consideration. And a CDF chart is one way of doing that, because those engines which are still working influence the CDF estimate for each data point. So if we can see, for example, a data point, the third one from the right, the third highest one, has a CDF estimate of about 62%. Now, that is influenced not just by the other 27 engines that have failed, but the 50 that haven't failed. And we cannot ever throw away information. As soon as we throw away information, simply because, for example, those engines haven't failed. We introduce bias into our data. We don't want that. Now, Weibull plotting is a really useful way of transforming what we've just seen into another way of visually representing the data. Now, I've done plenty of webinars on what a Weibull plot is. Now, I'm not going to go into it in great detail, but suffice to say, a probability plot involves a chart which is especially scaled in a way such that if the data followed an underlying distribution, it would create a straight line. So the Weibull distribution, which is a distribution we use a lot in reliability engineering, which we'll go into a great bit of detail later on, will generate this particular Weibull chart. You can see in the horizontal axis, you have usage or time expressed on a logarithmic scale. Every step increase, or every time you increase usage by a factor of 10, you move the same distance across the horizontal axis. So you go from 10 to 100 to 1,000 to 10,000 to 100,000 in equal steps. And the vertical axis, the CDF axis, it's a little bit different, the scale, and we won't go into the details about how you get that particular weird looking scale. You can see that the 10% estimate for CDF is about halfway up the chart, as you can see it here, and 99% is almost double that. So there's a weird scale thing going on here. You can see that the scale is very spread out at the bottom, 0.2, 0.3, 0.5%. It's also starting to spread out at the top. In the middle, the distance between 40 and 50% is very, very narrow. But at the top and the bottom, the distance between, for example, 99 or 98 and 99% and 1 and 2% is very large. This is a Weibull. So this is a Weibull plot where that time to failure data has been plotted in a way which helps us look at this chart and hopefully work out what's going on. So one of the many questions we might ask ourselves was, what might be driving failure? So if we look at this Weibull plot here, is anyone brave enough to hazard a guess just by looking at this chart what might be driving failure? Anyone want to put in the chat window what they think might be causing the failure of our big engine for our mining truck? Fatigue. Why is that, Kevin? Changing engines based on hours, that's a strategy. You can change engines based on hours, but that is in response to a failure or perceived accumulation of damage. So that's not sort of what's driving failure. That's a response to failure. Anna says we likely have multiple failure modes here. Okay, I'm going to ask Anna, why do you think there's multiple failure modes? Because the line is not straight. That's really, really good. So I can see other comments are that there is, looks like there's wear out failure. On the left-hand side, it could be due to manufacturing defects, which is not wear out, but by the same token, some people believe there is wear out going on. But Anna says you likely have multiple failure modes here because the line is not perfectly straight. Now, many Weibull analyses I've seen simply take this data and they try and fit the line of best fit and say, well, we're done. But that's not really good. In fact, what we should always do, if we see this line which isn't straight, try and extract information. Now, for this scenario, we're able to get data as well, and we're able to identify that 3 components were causing the majority of failures. And you can see here, I've replaced the blue circles with different shapes and colors for different components. These components are systems in their own right. So for example, don't forget, this is a huge engine, and the scavenge pump, which is times to failure represented by these red triangles, they're substantial subsystems in their own right. So what we can do is we can simply replace those blue dots on our Weibull chart, a Weibull plot, I should say, with different symbols for specific components. So you can see straight away that these scavenge pump failures appear to be at the right. They appear to be occurring at the end of our data set. And in fact, what we can do is essentially say, you know what, let's just focus on the scavenge pump and nothing else. Let's assume let's turn every other blue dot into a right sensor data point. Why we do that? Because the blue dot represents some other component failing. It could be the valve train or the bottom end, for example. And when that engine failed due to another component failing, the scavenge pump at that point in time was still happily working away. So from the perspective of the scavenge pump, that is a right sensor data point. So we can create a Weibull plot for our scavenge pump and nothing else. And this is what we get. Now we can use computers and science and math to create this thing here called a 95% confidence interval, or confidence region perhaps. And this represents based on our computer being told to assume that there's a Weibull distribution describing this particular data set. Given that we are assuming the Weibull distribution is the overarching way of describing times of failure, given these 6 data points, and don't forget 72 sensor data points, what do we think the confidence interval on the true CDF might be? This represents the region which we believe the true CDF line exists. So this is quite interesting. So does anyone, given this particular chart, want to hazard a guess as to what might be driving the failure of our scavenge pump? Who's going to have a go at trying to work out what can we deduce from this particular Weibull plot? David suggests wear out. Seems like wear out, according to Kevin. Now, for some of us who go, where are these people getting these conclusions from? Correct, increasing failure rate, Kevin clarifies. Well, the useful thing about a Weibull plot is that if we were to draw a line of best fit, which our computer can help us do, Doug points out the beta looks to be pretty high based on the left upper corner, and he's absolutely right. We move our line of best fit across such that it's parallel to the original line of best fit. We get this thing called a beta value of 8.96, which is one of the parameters of the Weibull distribution. Now, again, this webinar is not going to teach you everything there is to know about the Weibull distribution. There's plenty of Ascendo courses and webinars to help you out with that. So what does this figure for our beta parameter tell us? If anyone has any familiarity with Weibull probability plotting and the Weibull distribution, Doug is hinting that it looks pretty high. What does high mean when it comes to the shape parameter or the beta? A large beta usually indicates wear out. Absolutely. So when it comes to Weibull probability plotting or Weibull distributions, when the beta parameter is greater than 1, which is actually the slope of the data on a Weibull plot, it indicates wear out. And wear out is simply the accumulation of damage. So I think someone mentioned fatigue earlier. So there's a bunch of different failure mechanisms which are all about accumulating damage. Damage can mean that our fatigue crack is growing. Creep deformation is getting bigger and bigger. Our elements is slowly diffusing across the dielectrics, etc., etc. If we're experiencing wear out failures, what can we do to mitigate, prevent, address, respond to these sorts of failure mechanisms? Kenneth mentioned preventive maintenance. That's fantastic. And the reason why it's fantastic is preventive maintenance, all it does is remove damage. More grease, which is let's call it a subset of preventive maintenance. When we do preventive maintenance, the preventive maintenance is triggered by intervals of usage. So you might, for example, every 6 months, get Kevin out to our engine and ladle on more grease if that's what it takes. And the idea is by putting on more grease, we remove damage. And damage can be quite broad. For example, losing grease or having grease contaminated with shavings or dust and debris is one form of damage. So when Kevin adds more grease, he either replaces grease we've lost, which is one form of damage, or he replaces grease that is now substandard, another form of damage. And so when we accumulate damage, we can do things like preventive maintenance or condition-based maintenance, which is similar to preventive maintenance in principle. It's just that as opposed to doing it at set intervals, we have some sort of sensor that is able to detect the amount of damage. And we only then do maintenance once a trigger level of damage has been crossed. We can also, if we model this particular failure mechanism, we can work out the warranty reliability or predict or calculate optimal warranty periods. Perhaps if this is a big deal, if this is something we can't maintain, and that particular wear out failure mechanism will then drive the service life of our machine. But more importantly, if we're able to work out which things accumulate damage the most, these become the vital few things we need to worry about. William suggests we can use wear barriers design, which is a great idea, a lubrication, surface treatment, all these things, which essentially what you guys are saying, which is fantastic, by the way, is things that are either going to, one, reduce/slow the accumulation of damage, or two, address the amount of damage that we incur and otherwise reset it or remove it such that it's back to some sort of predefined, undamaged state. And that's one way of really keeping up the serviceability of our equipment. And so we actually sort of have already come up with lots of different ideas to address our scavenge pump failure. We can obviously do things like redesign. Every failure we can redesign as an option too, if things wearing out too quickly. For example, if the scavenge pump is the only thing wearing out on our engine, then perhaps we can source a more robust scavenge pump and extend the life of our engine. Okay, so that's one of those components which appear to be failing more often than not. So another component we're going to look at right now is the bottom end, and these green squares represent the bottom end times to failure. So engines that failed when the bottom end failed are now represented by these green squares. Now we're going to do the same thing, turn all the other data points into sensor data points and create a Weibull plot based on bottom end failures only. Here is the 95% confidence region that our computers have calculated for us. So what, if anything, can we deduce from this Weibull plot for our bottom end? So remember, the top left-hand corner is one way of helping us work out the slope of our line of best fit. And as we talked about in the previous example, a high beta value, a high slope value, that's all the beta is the slope of the line that our data traces out. If it's greater than 1, it implies wear out. What can, if anything, can we conclude? Slower wear out than previous, but beta is still greater than 1. Fantastic. That's what Kevin is deducing. Cannot disagree with that. Anybody else? No worries. So either everyone else is afraid or everyone else furiously agrees with Kevin. So Brian suggests it's close to 1, which is getting close to random, which is interesting. And I can't disagree with that. Looks to be more of a useful life failure mode when thinking of the old bathtub curve, slope close to 1, random failures. Just to be clear, every failure is random. Wear out failures are random. Wear in failures are random. Infant mortality failures are random. And these failures are random too. I believe what you people are saying when referring to when it comes to random is that these failures are occurring based on randomly occurring external events. So let's come back to this concept later on, because you guys are making some really useful deductions. We're going to draw a line of best fit. We're going to move our line across to this little scale at the top left-hand corner. And indeed, beta is greater than 1. So people wouldn't be wrong in concluding this is wear out because the slope is greater than 1. People would also not be wrong in concluding that this is relatively close to 1. Therefore, it means that we are having this phenomenon called constant hazard rate failures. Now, in practice, you guys have already come up with some really wonderful deductions based on already jumping ahead and deducing what this beta parameter is likely going to be. In practice, if beta is less than about 1.5 and it's close to 1 like this is, it usually means we're experiencing a constant hazard rate. Now, the reason why it's still greater than 1 in this case, or it's always going to be greater or less than 1, because this is a random process. We still have, I believe, 6 data points out of the total of 78. So no matter what, you'll never get a perfectly a line which has a gradient of or slope of exactly 1 when we're looking at field or test data. So you need to use a bit of judgment. And as a rule, if it's if it's less than 1.5 and if it's greater than 0.8, that usually means it's just a statistical artifact which is pushing this thing away from a value of 1. So if you see a slope that is 1, we have what's called a constant hazard rate. And a constant hazard rate means that whatever is driving failure is just as likely to occur for a really old system as it is for a really young system. So think of Cristomo just mentioned that random for him means random causes, therefore neither a process issue nor wear out. You could also argue that the process issue, which is analogous, for example, to manufacturing defects, that is also random. Wear out is also going to be based on, for example, random defects which naturally occur or random impurities. But I take your point. The causes are going to occur randomly with respect to the life of the system. So think about a building and a category 5 F5 tornado. It doesn't matter how old or young that building is. If it gets hit by a category F5 tornado, it's going to fail. Not only will it fail, it'll be picked up, crushed down into lots of little pieces and carefully distributed across a region that could approach hundreds of miles. It doesn't matter how old or young your building is, that building is going to fail if it gets hit by such a massive tornado. So we see constant hazard rate failures caused by catastrophic environmental stresses, lightning, tsunamis, tornadoes, spikes on the road for our tires and wheels that get punctured. Also human error and accidents, because if human errors and accidents occur randomly with respect to the age of a system or a machine, then it doesn't matter how old or young that machine is, that human error or human error / accident is going to appear to occur at a constant rate. Doesn't matter how old that machine is, doesn't matter how young that machine is, those sorts of failures will occur with that constant hazard rate. So let's have a look at our data again. In this case, you can see where all the bottom end failures were occurring in respect to the overall data set. And in fact, in this scenario, root cause analysis identified that contaminants in the lubrication were randomly critically damaging the engine. All it meant was these contaminants would essentially plug up quite randomly. Didn't matter, they didn't accumulate. It's got one bit of contaminant would take out the engine. So it's quite sensitive, unfortunately. But the root cause analysis backed up the deductions we just made regarding the nature of failure. And so given this sort of failure mechanism, what would you recommend? What would you suggest could address bottom end failures, which appear to have a constant hazard rate? And we have a root cause analysis which showed that it was contamination driving these constant hazard rate failures. What could we do? Anyone got any ideas of what we can do for our engine to improve its reliability? Great answer. We can start adding a filter to prevent those contaminants from doing something. Redesign, so adding or changing filters, fantastic ideas. Oil change, fantastic. So I dare say William Memento type filters as well. Now, I don't know if you've noticed something, but it's what has happened in this chat is quite profound. We have come up with some very targeted, what we call corrective actions based on a combination of data and root cause analysis, regular maintenance using a checklist, better quality lubricant. And all of a sudden, we have corrective actions if we were to, for example, get better quality lubricant, to install filters where possible, to look at our maintenance regimes, etc., we would almost certainly have a drastic increase in reliability, because the bottom end failures were actually the most dominant failure modes when we group them in terms of components or subsystems. Brian asked, where is the contamination coming from? Maybe better to address the source. Fantastic. Now we're starting to talk about making reliability happen. And we can't come up with answers right now because the engine's not sitting here in this webinar, but you guys are starting to ask fantastic questions, which is going to make improving reliability that much better. And William points out lubricant storage. Maybe there's something going on with the quality of the lubricant we put in, because it's a fair point, because we often have mining sites across the world in relatively inhospitable environments, and sometimes we need to store spare parts and lubricants in less than ideal situations for a long period of time. And that has often caused all sorts of problems that people weren't anticipating, because they just assumed that even if they left it in 50-degree heat for 3 years, that lubricant would be good to go when they needed to use it. And of course, that assumption rarely holds true. So now we're going to look at the last component which drove a lot of the failure modes, and this was the valve train, which you can see the times to failure data points for our valve train are represented with yellow crosses on our system Weibull plot. So now we're going to do exactly the same thing. Turn every blue data point into a right sensor data point, which will create a Weibull plot just for our valve train. And with the help of computers and science and math and integrated circuits, we were going to come up with this 95% confidence region. Now, this is starting to get a lot broader than what the other ones looked like, I should say. Now, don't be too concerned about this. One of the reasons it looks a lot broader is because we're starting to exist in the lower ranges of both time or usage and CDF value. So even though the bottom left-hand confidence interval looks very, very, very broad, if you look at the bottom left-hand corner of our chart, it's still going from, of course, something greater than 0 to 1%. So this, in a way, the Weibull plots have a magnifying glass at the bottom left-hand corner of our chart in particular, and to a lesser degree, the top and the bottom of the charts as well on the left-hand side. So yes, the confidence interval is wider, but there is some statistical artifacts for that to occur. We can see some people are already jumping to the answers to the question I'm about to ask. But I'll go back to Carl's question, which I've just noticed. Is human error an independent or dependent variable when it comes to the reliability of equipment? Well, it depends. If human error is not going to be based on the age of the equipment, then it's independent. But however, let's just say that for whatever reason, equipment deterioration actually contributes to human error. Sometimes that can be down to gauges which aren't as accurate as they once were. And if we make decisions based on those gauges, if the gauge is 10 psi, says it's 10 psi when it's supposed to be 12, but at the start of its useful life, that gauge was very, very accurate, then a human might make a decision based on that information, which turns out to be wrong. And you might actually, instead of classifying that as human error, may actually reclassify that as a failed gauge, which became the root cause of that particular failure. But of course, when things get older, they can sometimes just be harder to operate. There's vibrations here, there's more noise there. It shakes a bit more than usual over here compared to a brand new one. And so sometimes when the machines get older, it might elicit human error. Another way I think older machines can elicit human error is if the training or the people who built that machine or introduced that machine into service have since left the company, and you have a new fleet of human beings coming in to operate that machine who aren't as familiar with it as the old guard were, the OG. So to an extent, the probability of human error increases as that machine ages, but in a very indirect way. So without answering your question specifically, you have to look at what might be behind human error. No worries. So we have already, people have already answered the question, what might be driving the failure of the, what's this one? Is this a valve train I'm up to, I believe? And so people have, Keith said early failure, quality. Kevin suggested defective parts. William suggested infant mortality. And also suggested errors in process that aren't random. And I think Carl suggesting as an answer, operator training as it relates to reliability. I might come back to that one, Carl, if you don't mind. Well, I dare say most of you are coming up with these figures or these answers because the slope that the data appears to plot out is getting shallower and shallower. In this case, the slope, if we use our beta scale up here, the beta parameter is about 0.73. So you guys are obviously been learning very, very quickly, or either have an impressive amount of knowledge before today's webinar. You've already worked out, because this beta value, the slope is less than 1, we are experiencing wear-in or infant mortality. Now, what these sorts of failure modes mean is that there is a subset of systems or components or products which are, let's just call them imperfect. And those imperfect components and products and systems are going to have things like defects or anything else that makes them less than optimal. And these product systems components are going to fail early. And so what that means is that the machines, the components, the products that are left are more reliable because they are unlikely to have survived through that initial period if they have those defects. So if they do survive, they tend to not have those defects, which means they're more reliable. So the apparent reliability of your fleet or population increases as at least initially, as your thing gets older. And wearing can be caused by all sorts of issues. It could be interface issues, software bugs, which software can get fixed pretty quickly. So it appears as if your software is improving reliability, assembly or installation error, manufacturing defects, damage during transit. And what these things do is, if we put software to one side, is these create damage or defective or otherwise imperfect product systems or components in a fraction of the total population. Software is different because we usually have a team that's going to remove those bugs as and when they occur. So in a way, the population of your software, which is usually one software program, becomes more reliable because those defects are getting removed by a software debugging team or a software patch team. When it comes to mechanical systems, the mechanical systems are becoming more reliable because the defects are being pulled out as those defective components fail. So wear-in or infant mortality is usually synonymous. What can we do if we're experiencing wear-in or infant mortality? What are the things we can do to prevent those sorts of failures? What can we do if we are seeing infant mortality or wear-in? Better training, stress screen or burn-in before sending parts out. Test to an extent. Testing is can be all sorts of different types of testing. Quality check improvement, burn-in, ESS, which is stress screening. I see Doug's responding to Carl's question. We'll come back to that one. Inspect. What's going on with these 3-word responses? Oh, but I see where it's all circling around some basic ideas, which include statistical process control, which I like because that's very proactive. It's all about keeping your machines, your manufacturing machines, doing what they're supposed to do within your specification limits, like well within. As in, if anything starts going wrong, it's going to take a while before they start creating defective components. Descreening is another approach, but that essentially deals with manufacturing processes which create defective components. Statistical process control is ensuring your manufacturing machines don't create defective components in the first place. Training, especially when it comes to installation or assembly errors, and manufacturing, of course, and burn-in. Burn-in is a testing approach where we can get components just being manufactured, use them, or otherwise test them in some sort of representative test bed to get those defective components to fail early. And we assume that's whatever's left is now going to be much more reliable. So we've already come up with a wonderful range of ideas for our valve train. And in fact, when we did the root cause analysis for this valve train, the issues came down to an installation issue. So you can see straight away that these deductions from Weibull plotting align with what is going on in the real world. And if you're able, as a reliability engineer, to look at a chart which doesn't create a straight line and then say, you know what, there's something more going on in this chart than meets the eye, and start just scratching the surface, you can come up with some really useful recommendations, which you guys have just done based on nothing more than where these dots lie on a Weibull plot. Again, many Weibull plots or many so-called reliability reports will get a data set like this and say, and the alleged reliability engineer responsible for the deductions will essentially say, you know what, this line's straight enough. I'm going to put a single straight line through it, come up with a beta value, which in this case would be close to 1, because you have wear in, wear out, and a constant hazard rate. So if you just simply fit a single straight line to this data, you'll say, oh, our engine is experiencing constant hazard rate failure. There's no wear out. We can keep using it indefinitely. And that is a problem, as we can tell, as we just worked out, because it appears as if our valve, no, what is it? Which one's the red triangles? I've forgotten. What was it? Valve train was the last one, bottom end. The pump. Thanks, Fred. The scavenge pump. The scavenge pump is actually going to tell us when our engines give us essentially the end of our service life of our engines. We need to do something to our engines before that scavenge pump starts causing all our engines to fail. Or we can extend the service life of our engines by looking at the scavenge pump. So that's what it is. That's what Weibull plotting should be all about. Getting this data on the screen, and then not just by default trying to put a single straight line through it, but trying to pull information. We can see that this is the constant hazard rate slope. We know that this region here is the wear-in slope, where if you see data which has a shallower slope, it usually means there's wear-in or infant mortality going on. This is the slope for wear out. And our line of best fit, so to speak, actually has, you would argue, an element of each one. Now, it's not perfect, but you can see that there is this sort of curvy trend going on. And that is essentially the bathtub curve, where it's shallow at the start. It's not going down. It's not a bathtub unless you look at this bathtub curve, something that's very shallow and sort of tilted up. But where it's shallow at the start, that's infant mortality. Where it's steep at the end, that's wear out. And if you've got a bit in between, you might have a constant hazard rate. But what about a system which is lot simpler. It's all well and good looking at a textbook which says, yes, the bathtub curve has this wonderfully smooth decreasing hazard rate at the front. It has a wonderfully smooth increasing hazard rate at the back. It has this very flat bottom every single time. Every single bathtub is exactly the same. Well, I'm going to challenge you guys because we're going to look at a very simple machine, a semiconductor laser diode. Now, this is simple, but just because it's simple doesn't mean it is simple to make. So this is a diode which is based on a non-silicon semiconductor. But what it does is essentially turn electrons. It doesn't turn electrons into light, but it will generate light from electricity being pumped through this diode. And so you have this diode made out of a single semiconductor, which is essentially, ideally, a single crystalline structure. That is, all the atoms are joined in a precise lattice throughout the entire size, entire volume of this chip. Now, this is a relatively small part of this component, but from the molecular scale, it's pretty massive. So our manufacturers are always striving to create single crystalline structures in this little part of our laser diode. But of course, Mother Nature doesn't always let us do that, even if we have the best manufacturing scenarios. So so there is a chance that this is going to experience some sort of wear-in if we understand what's going on. But what else happens for is anyone who has worked in the electronic component industry, what sort of failures will typically drive semiconductor failure? What sort of underlying issues will cause our electronic components to fail eventually? Heat, solder joints, heat. Let's go back to heat. What does heat drive failure? Wrong orientation of the board. Yep, that's yep. Moisture ingress, vibration, diffusion. Arrhenius. Arrhenius refers to a dude who came up with a pretty interesting model. Essentially, what you guys are coming up with, you're talking about damage being accumulated. When you have heat, what does heat do? It actually accelerates chemical reactions. And so this wonderfully, beautifully close to perfect crystalline structure, which comes off, which we get when this comes off the manufacturing belt, so to speak, eventually it's going to degrade through diffusion. It's going to degrade due to maybe some dendritic growth, whiskers. Essentially, all electronic components do accumulate damage over time. Voltage accelerates degradation. Temperature accelerates degradation. So everyone we're talking about, now Fred's just, he's having a failure mechanism salad in this chat window, but none of that's wrong. All these things, these radiation, for example, is another way that another thing's going to cause damage in these relatively small but simple electronic components. So this is very different to our engine for our mining truck. There might be thousands upon thousands of plausible failure mechanisms for that engine. You can imagine there's everything from lubrication through to electronics, through to paint, through to wear, through to creep, through to fatigue. Whereas for this particular laser diode, even though it's a pretty sophisticated bit of kit, it's comparatively very simple. And the failure mechanisms at play, we still mentioned quite a few in this chat window, but it's a lot smaller group than that applies to our engine. So let's just say we did let's not just say it, we did some actual time to failure testing for this laser diode. And when we create a Weibull plot for the time to failure data of our laser diode, we get this. So what can anyone deduce from this chart? What can we see? Can I suggest it's random? Beta is close to 1. Yeah, all right. Happy with that. Multiple failure modes from Kevin and Sebastian. Okay. Multiple failure modes, sort of like our engine. So Doug says it's not perfectly straight, so likely a couple things are going on. Another way of saying this: multiple failure modes. Multiple failure modes by 3, says Brian. But what's different about this? We looked at the Weibull plot for our engine, and there was clearly a region. William suggests there's 3 breakpoints. There's clearly a region of infant mortality at the start with a shallow slope, and wear out at the back end with a steeper slope. Is that what's going on here? Do we have infant mortality at the start? Kevin says there is no infant mortality. Okay. Anybody else? Or an acceleration mode, says Karen. Interesting. Seems like 2 wear out modes, says Kevin. So I'm going to add a couple of visual aids. It depends on which failures have what failure mechanism. That is true, but that's a general statement that applies to everything. You don't have a time axis. Oh, I mean, we do have a time axis. You can't see the numbers, but it doesn't mean that you cannot work out which part is the early stages of the life. So it wouldn't matter if it's 1, 10, 100, or 1,000, or 1 million, 10 million, 100 million, or a billion. You can definitely see something going on with respect to the overall life of the system. So Kevin actually said 2 interesting things. There's no infant mortality, but there's 2 wear out modes. So let's help you guys out a little bit. And I'm going to put 2 lines. Now, these lines have the same slope. They both have beta values of 2.0. Now, given that I put these 2 lines in, does that help us get to the bottom of what's going on? The diode manufacturer is different, the auto example, because it is at a more granular molecular. It is more granular molecular. Yes. Kevin suggests those are the 2 wear out failure modes that's going on. Interesting. So if there are 2 wear out failure modes, why does the first one stop? Why do we only see the first one? Why do we see like a smaller wear out failure mode at the start, and then it all of a sudden goes to this wear out failure mode at the back? What does that mean? What's going on there? Might have 2 subpopulations here. I like it, Andre. Keep going. Growth in population, not quite. No, it's not just going on. The same population was under test. They're all essentially, for all intents and purposes, from the same manufacturing process. Different suppliers, no. There's one supplier. The early phase might have been exposed to a stressor that the others were not. No, I can rule that one out too. The testing was good. Different batches, no, it's not that. Possibly. But what's going on here? All the weak parts have failed at the beginning. Andre, I like where you're going with this. Not differences in usage. So you just, all intents and purposes, you can assume the test was pretty damn good. Well, I'm going to show you something which might help you. Andre suggests it might be a good candidate for Bernie. You're coming up with some pretty insightful stuff, Andre. I like it. So I'm going to show you what we can do is if we assume we have what's called these early wear out failures. And what I did was I created essentially 2 Weibull distributions, one which fit the early wear out failures and one which fit the later wear out failures. And as a rule, when you see some simple components, this sort of thing happen, the beta parameter, the slope, stays the same. And so what I did was use my computer to help me out. And we came up with a model where the early wear out failures were only occurring in 3.3% of all the diodes. And the remainder of the diodes have these later or end of service life wear out failures. And you can see the CDF curve we get from this combined model. This is not just a line of best fit. This is a model where we have early wear out failures applicable to 3.3% of all diodes. And then the remainder are subjected to this the secondary failure, wear out failure. So what is going on? Why do we have early wear out in 3.3% of diodes? Why is that the case? Why is that the case? Why are only 3.3% of diodes material defects? A good idea, Kenneth. I think you're right. So what this suggests, manufacturing errors, contamination or assembly errors. So essentially, some of the comments that have come through where we have two distinct subpopulations are essentially true. About 3.3% of all diodes have some defect. And that defect, because remember, this is a simple system. When that defect is present, which is not unusual for dielectrics and semiconductors, this is not necessarily the result of bad manufacturing. It's just that it's damn hard to create perfect crystalline structures in diodes. So 3.3% appear to have some sort of defect which triggers the wear out that would otherwise occur a long time later on. And that's that horizontal axis, don't forget, is in the logarithmic scale. So the wear out failure modes that would otherwise occur much later are actually much later, even though on this chart they don't look like they're that much later. They are or at least an order of magnitude later because of the logarithmic scale. And so we don't actually have three things going on. We actually only have two. And what it looks like, the bit that joins these two straight lines is actually the region where they transition from the last remnants of those defective diodes failing, and then we revert to, let's call it the service life wear out, whatever you want to call that secondary wear out failure mechanism. So essentially, this is a scenario where you actually have infant mortality that appears as if it's behaving like it's wearing out. And the reason why that's the case is because this diode is a simple component, a really simple component which does not have the plethora of failure mechanisms that that engine for our mining truck has. And so we often see curves like this for simple systems, simple things like a laser diode. And that usually means that there is infant mortality, but that infant mortality triggers a very specific failure mode, a wear out failure mode, that if that defect wasn't there, would naturally occur later on. And so that early wear out tends to have the same slope as the wear out that would occur, let's call it naturally. And sometimes it looks like we have this three-phase approach to the life of this component. We actually don't. We actually only have two, and we have this region of transition between those two phases. Now, Andre suggested this would be a good candidate for burn-in. Love your responses. And the reason why is because we have infant mortality, even though it's behaving like it's wearing out. And so once we have this CDF curve for our data, and hopefully you'll agree with me, this appears to fit the data really, really well, we can calculate how long we should burn in. So for example, if we want to burn in this this diode for 30,000 hours, this would be, the dotted line represents the CDF curve we'll be getting in response. So you can see that we pushed it way to the right, which is, and as a rule, you might be interested in your system, your LiDAR, for example, might become obsolete or might be beyond economic repair when 1% of your diodes have failed. And so you can see that we have almost, if we're interested in the time where we expect 1% of our diodes to fail, we have increased our service life by almost an order of magnitude if you look at that 1% line. Now, William suggests that flat portion looks random, and it does look random if you're going to look at it from a very statistical perspective, in that there is, yes, one part of that transition part where we have constant hazard rate failures. But we know they're not happening. We know they're not happening for this diode. There's a test regime, and the voltage is very well controlled. And the model we came up with, which fits the data very well, it didn't need to have a constant hazard rate element for us to get this line of best fit here. And so that's why we always need to scratch the surface of our Weibull plot. So if you ever have a really simple system, might be sophisticated, but it still might be simple, and you don't get that sort of bathtub curve shape, then there might be something else going on, like this early wear out, which is still technically wear in, even though it's called wear out. Now, Brian points out that that is a 3+ year burn-in. It's actually well more than 3 years. It's because there's about 8,700 hours each year, so it's almost 4 years burn-in. But of course, as you point out, you can accelerate burn-in, especially for electronic components. So that means we can either increase the voltage or increase the temperature to replicate 30,000 hours of burn-in in a much shorter period, as Kenneth points out. So Maximilian asks, if we're going to present this option of burn-in to upper management, does it make sense to propose a cost analysis of performing the burn-in and scrapping versus warranty costs? And the answer is absolutely yes. We can now work out that in this case, if we do equivalent of 30,000 hours, obviously accelerated, we can't do burn-in for almost 4 years, that the time by which we expect 1% of our things to have failed go from what looks like about 8,000 hours all the way up to 20, 30, 40, 50,000 hours. That's a huge, which is what this chart suggests. That is a huge improvement, a massive improvement. If that's the B1 life is what matters the most. The B1 life is the time by which we expect 1% of our things to have failed. And so you can work out, okay, well, that's going to save this many warranty failures in the future, and that's going to save us X million dollars or what have you. We work out how much burn-in costs or how long it's going to take. But all of a sudden you have a business case which writes itself. Managers and bosses hate reliability engineers who go to their office and say, you need to do this. And they ask why, and they say, well, you just should. You just have to. It's going to work. Just trust me. This doesn't work. But now we have a curve which says, hey, you can do 30,000 hours of accelerated burn-in, so maybe you can replicate that in a matter of weeks. And that means we will improve our B1 life for our laser diode from 8,000 hours to 50,000 hours. Your management's going to listen to you. They might, if they decide to go against it, perhaps the business case didn't work out. But even if that's the case, now they're making an informed decision. But that's what we're all about. The important message of this lesson, I'm glad you asked that question, Maximilian, is all about what it is we're trying to achieve. I'm so glad that someone started asking questions which went well beyond just the statistics we are looking at and the probability plotting, and saying, well, what does this mean from a business perspective? That is, from, dare say Fred agrees with me, that is what we want to have happen more than anything else. People say, how can I use that in the real world to generate money or just make things better? So the real message of this lesson is to always focus on what it is that matters, the vital few. For example, this engine, 82% of failures were down to 3 components, 82%. The scavenge pump was the thing that was driving when this engine essentially became obsolete. It was no longer useful trying to keep repairing, because that was wearing out and driving all the end of service life failures. We have I think a scavenge pump that we came up with some really wonderful ideas about how we could reduce how those lubricant contaminants were causing those randomly occurring constant hazard rate failures. And of course, we quickly identified that the bottom end was the other one, the valve train, I should say, was the one that had infant mortality. So what was going on? Okay, so we'll do a root cause analysis. We don't focus on the design necessarily. We might focus on the manufacturing and installation, and lo and behold, we found something. So we're not just measuring reliability, we're improving it. It's all about the vital few. And if we look at the laser diode, for example, if the B1 life is what matters the most, well, if we're able to look at a Weibull plot, not just stick a simple simple straight line, which I think one of you pointed out, if we did, would imply a constant hazard rate, which would give us absolutely nothing in terms of the estimated improvements from burn-in, then we would miss an opportunity that Maximilian pointed out that we could exploit by doing the analysis, working out how much reliability improvement we get for a 30,000 hour burn-in, and present that to management and say, hey, we could perhaps revolutionize our warranty costs if we do this. Carl asks, or just states that failure rates and length of warranty of the equipment adjust the length of the warranty for minimum failure rates. Any thoughts? Just to be clear, failure rate is quite a broad term in terms of how it's used. Technically, it just means that, as a rule, failure rates tend to reflect, well, when they use the context of the person saying the failure rate, mentioning failure rate, is they're referring to a constant failure rate or a constant hazard rate. So I'd suggest that you're saying, Carl, that we can adjust the warranty to minimize the overall failure rate of the system. And I won't say no, but I can't say yes, because I don't know what the business proposition is. If it's simply a warranty thing, then as a rule, the only thing you're interested in is reliability. So your profit margins are based on, as a rule, not having to incur more than, let's just say, 5% of your fleet failing. That would then cause you to expend money on warranty action. And so you'll often have warranty reliability targets, which might be 99%. So you only have to repair 1% of your fleet, or 90%. So you have to repair 10% of your fleet, but usually nothing higher than 5%. When it comes to failure rates, you're talking more along the lines of asset management. If you and preventive maintenance, if your thing starts becoming more, if you keep using your thing such as the overall hazard rate, average hazard rate, so to speak, increases, that means that, for example, your scavenge pump is starting to wear out, so you need to fundamentally replace something in your system. There's no point replacing it over and over again, or repairing it because it's wearing out. It's not a universal truth, but that might drive the time you retire that part of your system. I don't know if that answers your question, because there's a little bit behind the context, which is not immediately clear, but hopefully I'm in the ballpark of stimulating some progressive thoughts. So it's all about the vital few. Now, any questions about what we covered today? Functional safety standards are actively using the term failure rate or fit rate in assessing safety integrity level. Functional safety standards, from my perspective, I've looked at a couple of them, Andre, and they are terrible, absolutely terrible. I've seen functional safety standards where they take failure rates, including fit rates, and they give you ideas for coming up with assumptions, which then drive when you expect things to wear out. So, for example, you'll see one functional safety standard in particular say, well, if the hazard rate is this, therefore you assume that I think it's times a mean time to failure by 1.5, and that's when you expect everything to wear out. It's just horrible, absolutely horrible. You can't do that. Oh, good. So you agree, and you've wrote a paper on this issue, which is, oh, my microphone just fell off. Bear with me. But yeah, so functional safety standards are supposed to reflect the most sophisticated approaches we have to ensuring safety into our devices, but it just has such a, the statistics they use are not even high school statistics levels. They're absolutely terrible. So hopefully that helps you understand my perspective on those standards. More proactive maintenance, less reactive maintenance. As a rule, yes. But again, too much proactive maintenance can drive down reliability, because every time you maintain something, you introduce those wear-in or infant mortality failure mechanisms as well. So more optimized proactive maintenance, absolutely agree. Condition-based maintenance, where the business case makes sense, fantastic. Preventive maintenance, where you optimize the interval, fantastic. The idea is to drive down reactive maintenance or corrective maintenance or repairs as low as possible. But that isn't always simply achieved by doing more proactive maintenance. I've seen many organizations overdo it to the extent that they cause more failures than they prevent. And that issue was a subject of another webinar I did, I think, last year, how you optimize servicing intervals. Any more questions? Did we enjoy just looking at a Weibull plots today and sitting back and having guesses at what's going on? Thank you, Carl. Thought it was fun, fantastic. I think you might be the first person in the history of the world who suggested a discussion on Weibull plotting was fun. But I'll take that, Kevin. Thank you very much. Thank you, Skylar. But yeah, so today was supposed to be, I should say, a simple webinar where we just talk about very typical Weibull plots. And it's not unusual for us to get data, which if we just spend 5 seconds more looking at it, we can actually get some really useful information. The number of Weibull plots, which I simply see have a straight line fit through it, and they say, oh, it has a slope of 1, therefore this engine is not wearing out, it's not wearing in. And you go, no, it's not the case. You need to look at how this data plots out the line this data plots. It's not straight. And just because it's not straight doesn't mean there's lots of information that you can pull out. So the notes are there that Fred has shared in this chat window. You'll also see the link to the notes in the webinar window on Ascendo. This is obviously being recorded. So for, sorry, I can't see the first name of the person who turned up late, but I understand we're all busy, so it's all good. But this is recorded, so you can go back to the very, very start. And there's that link again for the notes, but hopefully you guys got something out of it. It's a cheap, very average, ordinary reliability engineer who just does a Weibull plot to get the line of best fit. Data is telling you a story, and if you just want to listen to what the data is telling you, you can get some really useful ideas, such as giving a business case to your boss that would extend the B1 life of your laser diode from 8,000 hours to 50,000 hours just by doing some burn-in. That's the sort of stuff bosses and managers want to hear from their reliability engineers, not just a list of things that they need to do because the standards say so. So beyond that, everyone, thank you very much for your time. We'll see you next month.